Day 1 was on measurement. The first thing you need to know about measurement is the difference between accuracy and precision. Precision is how close two measurements are to each other, and does not take into account how close the measurements are to the correct measurement. Whereas accuracy is how close a measurement is to the correct measurement. An understanding of sig fig rules is also important in measurement. There are 5 main rules for sig figs. First, non-zero numbers are always significant. Second, any zeros between two significant digits are significant. Third, a trailing zero is significant only if a decimal is present. Fourth, leading zeros are only space holders and aren't significant even with a decimal point present. And fifth, exact numbers have infinite number of significant figures. Scientific notation is a great way to show sig figs. To be correct, a number in scientific notation must have only one digit to the left of the decimal point. In this example, 1.22 times 10 to the third is correct compared to 12.2 times 10 to the second. Day 2 was an analysis of matter. First, we must know the basics of the periodic table. There are 18 groups on the periodic table and 7 periods. There are 3 main types of elements on the periodic table: the metals, nonmetals, and the metalloids. Each atom of an element consists of protons, neutrons, and electrons. The number of protons is what determines what the element is. For example, whenever you have one proton in an atom, you know for sure it is a hydrogen atom. Isotopes and ions shape the atomic structure of atoms. An isotope of an atom has a different amount of neutrons but retains the same amount of protons, whereas an ion of an element has different amounts of electrons but retains the same amount of protons. There are 2 types of ions: negative or anions and positive or cations. Day 3 is all about nomenclature. There are 3 types of nomenclature: type 1, type 2, and type 3. Type 1 nomenclature is naming a compound that involves a metal and a nonmetal. In type 1, there's only one charge for the cation, and thus to name the compound, you name the metal and then name the nonmetal. But you must remember to take out the N of the nonmetal and replace it with "ide." Type 2 nomenclature is basically the same as type 1, but now the cation has multiple possible charges. Thus, when writing the name of the compound, you must add a Roman numeral after the cation to indicate the charge that you are using for the cation, and then you do the same as type 1 for the anion. Type 3 nomenclature is the naming of nonmetals only. To name type 3 compounds, you must add prefixes to the beginning of each nonmetal and replace the ending of the last nonmetal with "ide." However, remember to never add mono to the first element. To name acids, you must look at the ending of the ion or compound used. If the ion ends in "ide", then you add hydro to the beginning of the ion and then replace the ending with "ic acid. If the compound ends with "ate", then you simply replace the ending with "ic acid. And if the compound ends with "ite", replace the ending with "os acid. There are 5 main types of chemical reactions. Synthesis reaction is when 2 different substances combine with one another. A decomposition reaction is when a substance breaks into 2 different substances. A single replacement reaction is when one substance takes the place of another substance in the compound. A double replacement reaction is when all elements in a reaction switch partners. And a combustion reaction is when a substance combines with oxygen to produce water and carbon dioxide. In the double replacement lab, we tested different substances to see if they would react with one another. In order to tell if a reaction actually occurred, we looked for a precipitate, which is a solid, cloudy substance. This is also an example of a combustion reaction, where ethyl gas was combusted to form H2O and CO2.
Hi, it's Sarah. Kevin is having an aneurysm, so I'm here to voice over his video. Day 5. The mole is used to measure the amount of atoms/molecules in a substance. 1 mole of a substance is 6.022 times 10 to the power of 23. The molar mass is the mass of the substance divided by the amount of substance. To find the percent composition of an element, simply take the mass of the element divided by the mass of the entire compound and multiply by 100. An empirical formula is a simplified version of a molecular formula. For example, the molecular formula for ethane is C2H6, but the empirical formula would be CH3. Thus, because the empirical formula is a simplified version of a molecular formula, you cannot determine a compound based on the empirical formula, as it could have any amount of a certain element but still simplify to the same empirical formula. On day 6, we focused on limiting reactants and calculating percentage yield. Limiting reactants are the reactants that limits and determines the amount of product that can be produced in a chemical reaction. By knowing the limiting reactant, we can calculate the theoretical yield, and by knowing the theoretical yield, we can figure out the percent yield of a reaction by dividing the actual yield by the theoretical yield and multiplying by 100. Day 7 was focused on the atomic theory. The electromagnetic spectrum consists of gamma rays, X-rays, ultraviolet light, visible light, infrared light, microwaves, radio waves. The visible light spectrum includes red, orange, yellow, green, blue, indigo, violet, with violet having the highest energy and shortest wavelengths, and red having the lowest energy and longest wavelengths. When atoms are energized, the electrons within them also get energized, and as the electrons gain more and more energy, they move to the higher energy levels within the atoms. This is called excited state. When they drop back down to their ground state, they emit energy in the form of visible light. The higher the drop of energy levels, the higher the energy of light emitted. The lower the drops of energy levels, the lower the energy of light emitted. In the flame test lab, we used a Bunsen burner to energize the electrons in compounds to see the light of the flame they would give off when the electrons become excited and emitted light. The color of the flame gave us an idea of how much energy was emitted by the electrons. If it was toward the violet side of the visible light spectrum, the energy emitted was relatively high. If it was toward the red side of the spectrum, the energy emitted was
Day 8 was a continuation of the atomic theory. Electron configurations are used to describe the electronic structure of an atom. To do an electron configuration, you must know the s block, d block, and p block. S orbitals can hold 2 electrons, p orbitals can hold 6, and d orbitals can hold 10. To do an electron configuration, you simply go in order until you reach an electron. For example, if you wanted to do the electron configuration for neon, we would simply do 1s2, 2s2, 2b6. The number before the letter indicates a period, unless you are in the d block, in which it would be 1 less than the period. And the number after the letter indicates where in the orbital the electron is. Here are some periodic trends you should know. Electronegativity increases as you go up and to the right on the periodic table. Ionization energy also increases up and to the right. Atomic radius increases down and to the left, and electron affinity increases up and to the right.
Intramolecular forces. There are 5 main types of chemical bonding. Ion-ion is the strongest chemical bond and is the attraction between a cation and an anion. Ion-dipole bonding is attraction between an ion and a polar molecule. Hydrogen bonding is the attraction between molecules with HN, HF, HO bonds. Dipole-dipole bonds are the attraction between 2 polar molecules. London dispersion forces are the weakest bonds and are between all matter with large molecules. To do Lewis dot structures, 1. Determine the total number of valence electrons. Step 2. Write the skeleton structure of the molecule. Step 3. Use 2 valence electrons to form each bond in the skeleton structure. Step 4. Try to satisfy the octets of the atoms by distributing the remaining valence electrons as non-bonding electrons. Step 5. If needed, make double or triple bonds to satisfy octet. There are exceptions to these steps as well. Hydrogen only needs 1 single bond / 2 electrons to be satisfied. Halogens make single bonds only. Hydrogen and boron can be underfilled, and anything including row 3 or below can be overfilled. Lewis dot structures can help determine molecular and electron geometry by using the Vesper theory.
Intermolecular forces are the forces that allow for attraction and repulsion between different molecules. The higher the IMFs, the higher the attraction in the bonds. The lower the IMFs, the lower the attractions, which makes it easier to break the bonds of a compound. Intermolecular forces can affect many properties of molecules. As intermolecular forces increase, the boiling point and melting point of a thing increase. The viscosity increases, and the volatility or rate at which a compound evaporates decreases. There are also many types of bonding within solids. There are ionic salts that are bonded with ionic bonds, metallic solids, which are formed through the attraction of valence electrons and metal atoms. Network covalent solids are bonded through covalent bonds, and molecular solids are very weak and are bonded together by dipole-dipole and London dispersion bonds. Temperature is a measure of the average kinetic energy of all the molecules in a gas. Heat is the transfer of energy that results from the difference in temperature between a system and its surroundings. Specific heat is the amount of energy needed to raise the temperature of an element by 1 joules per gram Celsius. Basically, specific heat is how hard it is to heat an object. The specific heat of water is 4.184.
The kinetic molecular theory has 4 postulates. 1. The volume of individual gas particles is negligible because of their size compared to distance between particles. 2. Gas molecules are always moving randomly in the space they occupy at different speeds and directions. 3. Individual gas particles have a negligible force of attraction and repulsion when they collide with each other. 4. Gas particles continually collide with each other and the collisions are elastic, meaning kinetic energy is not changed. The idea gas law basically states that the volume V occupied by n moles of any gas has a pressure P at temperature T in Kelvin. The relationship for these variables is PV equals nRT. When the temperature of a sample increases, the pressure and volume also increases. This shows that temperature, pressure, and volume all have a direct relationship. Solutions 1. Solubility is a measure of the maximum amount of solute that can be dissolved in a given amount of solvent at a specific temperature. Solubility curves can help one see how soluble specific compounds at specific temperatures. Molarity is the ratio of the number of solute particles to the volume of solution. To calculate molarity, simply divide moles of solute by liters of the solution. Molarity in basic terms is a representation of the concentration of a solution. Redox reactions have an element that is being oxidized and an element that is being reduced. The element that is being oxidized loses electrons during the process, and those that are being reduced gain electrons. Dilution is the act of making a solution less concentrated. Solutions 1. On our second to last day, we learned about acids and bases, as well as equilibrium. Equilibrium is when a reversible reaction reaches a point where there is no further change in concentration of any species in the reaction. The forward and reverse reactions continue to happen, but the moles of any species in the reaction that are produced or used in a specific time period are the same, so the quantities of the reactants and products do not change. If you add heat or an element to the left side of an equilibrium equation, it will shift the equation right. If you take away heat or any element on the left side of the equation will shift left. This same logic applies for the right side of the equation. Acids and bases can be found along the pH scale. Acids all have a pH of less than 7, and all bases have pH of more than 7. The pH scale ranges from 0 to 14, with 7 being neutral. Strong acids quickly dissociate or split apart compared to weak acids.